Thank you, everybody. We're now having our third and final talk of this session. And I'm very happy to introduce Keisuke Hoshino, who's going to be talking to us about double categories of relations relative to factorization systems. So please, Keisuke.
Thank you for the introduction, and thank you to the organizers and participants for this opportunity. I will talk about the kind of relation between double categories and factorization systems as a first talk of the workshop by Miroslav, but from another point of view. This talk is based on a work with Hayatanasu, which is published on arXiv. So let's start. Firstly, recall that in a category with products, a relation in ordinary sense from A to B is defined as a monomorphism in C towards A times B. In the same way, a span from A to B can be seen as a morphism towards A times B. And in general, given class M of morphisms, an M relation can be defined as a morphism in M towards A times B. Moreover, one can define a cell of this form, as a morphism between the vertices of the spans, making this diagram commutes. So we found data like a double category, and indeed it gives a double category when M is the right class of a stable Rossonov factorization system. So let me explain how this works. So we say this letter EM. Recall that in an orthogonal factorization system is a pair of classes of morphisms, EM, satisfying these first three conditions. Mainly, they consist of the factorization condition and orthogonality condition. And an orthogonal factorization system is called stable if this fourth condition holds, which means the left class is stable under products. Okay, so on the other hand, a double category is a shared category internal to the two category cat. And I also write this part D0 by this notation VD, because I prefer to write tight morphisms vertically. And the double category is called an equipment if this functor, the pair of domain and codomain part, is a bifibration. So it has a Cartesian and off-Cartesian lifts. Since arrows in D1 here is a cell in this double category, the Cartesian and off-Cartesian arrow for this functor, this functor are just cells satisfying suitable universal properties. So in particular, if we consider Cartesian lifts of these forms, we obtain two ways to get horizontal arrows from a vertical arrow, and they are called companion and conjoint of F. And as a fact, these two horizontal arrows form an adjunction in the horizontal bicategory. So, so this functor for the desired double category letter EM is defined as a product along the binary product here, the binary product of the subfibration of the codomain fibration of C spanned by the morphisms in M. So now we have a pair of functors towards C, dom and chord, but And this extends to an equipment if M is the right class of an stable orthogonal factorization system. Let me mention the work by Schumann here. That this follows from the general fact that saying that if a bifibration is induced in this way, so induced from another bifibration by propagating along the product, and if this part is what is called monoidal BC bifibration, then the bifibration on the left here automatically extends to an equipment. And in fact, the M here is indeed a monoidal BC bifibration if M is the right class of a stable factorization system. Okay, so now we have a way to obtain a double category from an orthogonal factorization system. And one of the main results of our paper is the characterization theorem of these such double categories. So let me explain briefly about this theorem. So the first condition for the characterization here, which is called Cartesian equipment. So our double category is called an Cartesian equipment if it is an equipment and it equipped with a kind of Cartesian monoidal structure. So just as the fact that a Cartesian monoidal category is just a category with right adjoints to the diagonal and the unique map to the terminal. It is defined as an equipment with right adjoints to such functors in the two category of equipments. So it is a two category of equipments, pseudo functors, and vertical natural transformations. And this is observed in Verti's PhD thesis and later investigated in Aleiferi's thesis. And nextly, let me explain this Beck-Chevalier condition. So we say a Purback square or just a square here in the underlying category is Beck-Chevalier if the identity self in the square factors as an Cartesian cell following Cartesian cell. And this condition is intuitively related to discreteness. Indeed, discreteness. Indeed, in the double category of categories and profunctors, which is denoted by prof, a category is a discrete category if and only if all products towards this category is vectorially. So intuitively, this condition means all objects are discrete in a sense. Okay. So and the other condition in this line, in the same line, the strong tabulator is a special kind of double categorical limits. So given a horizontal morphism P of this form here, we say this triangle T exhibits A as a tabulator of P if it is universal among such triangles in this sense. So moreover, a tabulator is called strong if this T is op Cartesian. So obviously, this condition means that the horizontal morphisms is exhibits as spans in the underlying category. Okay. So now let me explain the condition on the last line. So we say a vertical arrow is a fibration if it appears as the left leg of a tabulator towards the terminal object. The condition is saying that such morphisms are closed under composition, and moreover, as a result, the right class M of the factorization system is recovered as the class of fibrations in this sense. So this completes the theorem, but how about the left class? So the left class is what we call final morphisms, which is defined as this bicategory condition. So for this square involving the unique maps to the terminals. And indeed, in general, for an equipment with strong tabulators and composable fibrations, final morphisms and fibrations form an orthogonal factorization system. So this is a generalization of what is called comprehensive factorization system observed by Strait and Walters. And indeed, in the double category prof of categories and profunctors, and this theorem gives the factorization system. So this explains why Strait and Walters gave this name to this concept. And indeed, the name is after the term comprehension system in logic, explaining the correspondence between types and terms, which is exactly the case when the double category is of relations. Okay. So returning to relations, the significant difference between the double category relations and prof is bicategory condition, so the discreteness. And with such discreteness, the factorization system becomes more simpler, so let me explain this. So firstly, let us restrict the bicategory condition. So we say a double category is discrete if these two canonical product squares are bicategory. So if a Cartesian equipment is discrete, the double category becomes Dagger compact, which means every object is self-dual. So intuitively, this condition means there is a symmetry in horizontal morphisms, and indeed, this implies that there is a duality of cells of those triangular forms. So using such duality, we can rewrite final morphisms. So because the final morphisms are defined as an Cartesian cell. So using this duality, we can make a symmetric version of final morphisms. So in this point of view, let me define inclusion and cover as follows. So the first one, inclusion, is defined by this Cartesian square, and cover is just a dual of the inclusion. So a cover is just a morphism equipped with an Cartesian cell of this form. So, and in the proof, inclusions are exactly free-face functors, and covers are what is called absolutely dense functors or Lark-shaping morphisms. And one might think cover as a kind of symmetric version of the definition of final morphisms. And indeed, work can show that in discrete Cartesian equipment, cover coincide with final morphisms. Moreover, if D has all bicategory products, final morphisms are stable on the products, and this makes comprehensive factorization stable. Okay. So let's go into the next chapter. So in the remainder of this talk, I will explain how properties of factorization system corresponds to those of double categories. Okay, this diagram is a Hasse diagram of the properties I will explain today, and the right one is exactly the properties for double categories of relations whose corresponding stable orthogonal factorization system has the properties on the left in the same position. Let me explain these conditions. So firstly, I will explain this part. In short, it says that the left class is included in epimorphisms if and only if the double category is what is called unique pure. So we say double category is unique pure if any cell of this form, so both top and bottom of horizontal arrows are identities, is trivial. So in other words, there's no non-trivial cell of this form. And moreover, this is equivalent to saying that the two category of vertical arrows is locally discrete. So, and this makes the characterisation theorem much simpler because this automatically induces the discreteness part, the vector condition. So in precise, any unique pair equipment with strong tabulators has vector products. So the proof is very simple. So suppose we are given a cospan here, Fg, of these forms, then we can construct a cell by taking the restrictions of the Cartesian cell here and then taking the tabulator. And then one can easily check that this square becomes a common square in the vertical 2 category, and hence a product square by unit pureness. And moreover, since tabulators are here, tabulator is strong, which means this cell is of Cartesian. So this square is vectorially. So on the other hand, one can also check that covers are co-free face in the vertical 2 category, which means precomposition of F like this is free faceful. And therefore it is an AP when the double category is unique pair because those two categories are locally discrete. Moreover, if D is a unit pure double category of relations, then the converse is also true. So we obtain this equivalence. So unit pair if and only if the left class, the final morphisms are APs. And moreover, so combining these observations, we obtain the following simpler characterization. So our double category is double category of relations obtained from an stable orthogonal factorization system whose left class is in epi, if and only if these conditions hold. So here, the vector condition is replaced by the unit pureness. Moreover, I want to note here that unit pureness also implies that inclusions, the dual covers, are also monomorphisms. And furthermore, inclusions are precisely monomorphisms when D is a unit pure double category of relations. And indeed, this is easy to check because being mono is the same as there's a product scale of this form, while being inclusion is the same as there is a product vector product scale of this form. So they coincide by unit pureness. So okay, let's get into the dual part. So the dual of E belonging epi is M belonging mono. So and this part is characterized by locally preordered double categorical relations. So let me explain this. So we say double category is locally preordered if cells filling in a fixed square is unique if it exists. And this condition is called flat in some literature. But on the other hand, observe that in any double category of relations, a cell of this form corresponds precisely with an arrow of this form, making this diagonal commutes. And this is because the double category is, well, firstly, it has horizontal duality, so it is Dagger compact. So cell of this form corresponds to the cell of this form. And then we can take tabulators, which is strong, then we obtain such square. So since this is the left leg of a tabulator, this is by definition a fibration. So therefore, if fibrations are monomorphisms, and such an arrow here is unique if it exists. So this shows the double category is locally preordered if the right class is monomorphisms. And the converse is also true more easy way. And this shows the correspondence between locally preordered double category of relations and factorization system whose right class is in monomorphisms. So, and moreover, one can consider locally positive double category as a locally preordered category, locally preordered double category, such that the vertical two category is locally positive. So moreover, one can check that for any discrete Cartesian equipment, being locally positive is the same as being locally preordered and unipure. So therefore, this implies the correspondence for proper stable factorization system. So a stable factorization system is called proper if and only if the right class is in M and the left class is in epi. Okay, so for this part, since regular epi mono factorization system is precisely a proper factorization system, whose right class is exactly monomorphisms. So we can obtain a characterization for double category of relations of regular categories. But since our approach is extending the work by Lambert in 2022, this precisely covers a result of this work. On the other hand, there is also a work by Carboni and Walters for this part, so double category. So in terms of bicategories, which is seemingly very different from our characterizations. And in our paper, we also give how the work is recovered from our general results, but I will omit this part today. Okay. So now let me explain this part. So when the light class contains all monomorphisms. Here, considering the duality of orthogonality, one can observe this condition is equivalent to saying that morphisms in the left class are strong epimorphisms. Because a strong epimorphism is the morphism left orthogonal to monomorphisms. So which explains why there is a line. So in finitely complete category, strong epimorphisms are epimorphisms. So and the corresponding property for this factorization system is what is called Cauchy condition. So to explain this, because that in the double category of profunctors, a category is said to be Cauchy complete if and only if any left adjoint towards this category in the horizontal. So in the world of profunctors is representable. So being representable in this double category is equivalent to being equivalent to some companion of an functor. So this leads us to the definition of Cauchy double category. So double category is called Cauchy if any left adjoint of this form in the horizontal bicategory is representable in this sense. So it is equivalent to companion. So in other words, a Cauchy double category is a double category such that all objects are Cauchy complete. So if we moreover suppose that D is a unit pure, this existential quantifier becomes unique existence, and because vertical two categories look discrete. And when a unit pure equipment is Cauchy, one can show that covers are left orthogonal to inclusions. So if this is moreover a double category of relations, since monos are precisely inclusions, as I mentioned before, and covers the left class, this implies that the right class 5 relations contains monomorphisms. So this in particular shows one direction. So the right class contains monomorphisms when the double category is unit pure and Cauchy. So for the converse, we can characterize horizontal left adjoint in unit pure double category relations as a horizontal arrow whose left leg of the tabulator is monic cover. This generalized the fact that a span is a left adjoint if and only if the left leg is an isomorphism. So utilizing this, we can show that a unit pure Cauchy double category relations corresponds to stable system whose right class contains monomorphisms. So, and let me note here that there is a similar work by Pavlovich, this paper, and we also gave in our paper a kind of refinement of his work. So in the next few slides, I will explain how the Kelly's work on the proper stable factorization system is treated. So Kelly in 1991 shows that relations for proper stable factorization systems is by category the same as relations for regular categories. More precisely, Kelly constructed a regular category from a proper stable factorization system and shows that the relations are the same. We gave a generalization of this work, so we established these blue lines and shows that the relations are the same. In terms of double categories, which we call causation. So given two unit pure equipments D and E, we say E is a co-serialization of D if the horizontal part is the same as E and same as D, and E is co-C and unit pure. Categorically, this gives a free object for the inclusion from co-C unit pair equipments to unit pair equipments. In other words, any double functor towards a unit pair co-C equipments here, U, extends uniquely to V here. So the unit pureness is essential for this extension using the fact that a companion expressing a left adjoint is in unit pair double category is unique. So more precisely given vertical arrow here in E, B, the image of F and V is the unique vertical arrow expressing U of F star, which is left adjoint. So so this implies that causation is unique if it exists. So, and for unit pair double category relations, we can show that the causation indeed exists and construct it as follows. So objects are the same as D, and the vertical arrow is an isomorphism class of horizontal arrows. So isomorphism class of horizontal arrows whose left leg of the tabulator is monic couple. And the cell of this form here is defined as a cell of the original category of this form. Moreover, we show that such causation is again a unit pair double category of relations. So in particular, this process makes the right class of an SOSS to contain monomorphisms. So this indeed covers the regularization process by Kerry because containing monomorphisms for the right class of a proper stable Poisson factorization system is the same as the factorization system is regular. And so in particular, this gives a well-known coarse object construction for a crazy topos. So lastly, let me explain about spans. Indeed, there are several works on characterization of spans. For example, that's by Walters and Wood in terms of bicategory, and the work by Aleiferi in terms of double-category. Although we have also a characterization of spans as a double category of relations in this sense, whose all morphisms are fibrations. Such characterization is seemingly very different from their works. The difference lives in kind of limits we used. So while we used tabulators, they are using co-identifiable objects for co-pointed endomorphisms or commonoid. Here by commonoid, I mean the commonad in the horizontal bicategory. So in the remainder of the talk, let me explain how the work is related to our results. So as I mentioned before, tabulator can be seen as limit of arbitrary horizontal arrow in this form. And this is the approach of us, and also by the approach by Lambert. On the other hand, Aleiferi uses a co-Eilenberg-Muir object of co-pointed endomorphisms. So the work uses limit of this diagram. On the other hand, Walters and Wood uses co-Eilenberg-Muir objects for commonoids. So it is just limits for this diagram. However, we show that in discrete settings, an endomorphism is co-pointed if and only if it is a part of commonoids. So co-pointed endomorphisms is essentially the same as commonoid, and moreover, such commonoid is the structure of commonoid is unique if it exists. And moreover, co-Eilenberg-Muir object for co-pointed things is the same as that for commonoids. And furthermore, we show that we can construct co-Eilenberg-Muir objects of commonoids using only tabulators when the double category is unique pure Cartesian equipment. So utilizing these facts, we also gave a characterization of spans using co-Eilenberg-Muir objects. So this explains to some extent how the theorems work. So this says that a double category is equivalent to the double category of spans for a finitely complete category, if and only if it is in pure Cartesian equipment. And it has co-Eilenberg-Muir object for co-pointed endomorphism or commonoids. And every morphism is a leg of a co-Eilenberg-Muir object. So it's equivalent to saying that morphisms are comonatic in a sense. So I think it's a bit short, but that's all. Thank you for listening.
Thank you very much for the talk. That was wonderful. And we now have some time for questions. So please, if you have any questions, either raise your hand, pop it in the chat, or simply unmute yourself.
Hello, thank you for your talk. I really enjoyed it. It's good to see this stuff again because I saw it once at CT and now I'm seeing it again now. It becomes more familiar to me. I'll ask you a question I asked you before because I'm interested to know if there's been any progress. When you define these vibrations, these morphisms as certain kinds of tabulators. Yeah, so there's a condition on the yeah, there's this condition that you have to ask that the vibrations are closed under composition.
Yes.
I think I asked this before, whether there's a way to sort of get this composition for free without asking for it explicitly via some other property.
I don't know any condition for this holds. So, but so I think in many cases, this condition holds, and moreover, I think some construction of the categories preserve this condition. For example, mod constructions. So okay. This might be helpful, but I don't know any more.
So in these particular double categories, you sort of use some other way of showing that they compose. So, for instance, in the double category of functors and profunctors, you would provide some equivalent definition of discrete vibration and show that this definition composes, right?
So
sorry, maybe that was a bit.
I don't any
yes.
the criteria for this condition holds.
Yes. Okay, thank you.
Okay, thank you. If anybody else has any other questions. Okay, if not, then I'd say thank you, Keisuke, again. Thank you for your talk.